In this video, we'll go over the paper titled Learning to Learn from Noisy Labeled Data. In short, this paper is a meta-learning paper which tries to increase the robustness of the trained model weights to the overfitting on the label noise. And the way they do that is that they synthesize basically additional noise. They add it to each batch as the model is getting trained on it and try to create an objective which tries to emphasize the parameters that are learned in a way that are not overfitting this synthetic label noise, and therefore in general trying to reduce the influence of label noise in the overall training pipeline. Say you have a dataset composed of n examples, xi being the example, for example, an image, and yi the label that is assigned for it, which could be noisy, meaning that it could be a label that is not corresponding to the semantics of the item xi. Say yi in this notation be the one hot representation of basically the class associated with xi. In this notation, f of xi given the parameter set theta is the output of the softmax layer for this network, basically the predicted probabilities. The conventional cross-entropy loss for it is written like this. And as you know, the cross-entropy loss is closely related to the KL divergence of the target and predicted probabilities. Now, their methodology involves a student-teacher setup to do this training. Once you get a mini-batch of data involving examples x1 till xk, alongside of them being the noisy labels y1 to yk, each one of them being essentially the one hot representation of the noisy label. Then they have a specific label alteration procedure which they run it like m times and get these basically new labels y hats that are essentially the original noisy labels plus a synthetic noise added to them. Now the way this synthetic noise is generated is that they select a row ratio of the batch and then they use the Euclidean distance of the representations, the latent representations that model has generated on each one of these examples. They basically find the top 10 items for each one. Let's say the batch size is like 128 or something. And then from these top 10, they randomly select one and basically swap the labels, therefore kind of retain the semantic information regarding, changing the labels as well, meaning the labels that they select to swap the labels with are kind of belonging to the examples that are semantically close because the Euclidean distance of the latent representations associated with those observations were also close. Now, for each one of these altered label set, they basically obtain these theta prime m, which is the one-step look ahead of the gradient descent for them. If you look at this, you have theta, which is the original parameter set of the student network, alpha the learning rate, theta the parameters. This is the conventional cross-entropy loss. You have x's, and you have this new label set with the same parameter set. Now, you also have a teacher model, which is using self-ensembling with this type of exponential weighted moving average. And they have added this consistency objective. And the reason why they chose KL divergence over something like MSE is that they figured that empirically it led to better results. The idea is that they take this representation, which is output by the teacher model, which is updated this way. They consider this to be the target, and this consistency regularization loss is going to make sure that for each one of these synthetic noises, it's not overfitted to that synthetic noise. Therefore, it's supposed to have like a good distance to the teacher's model, which are treated as targets. So again, the teacher one is the target, and DKL is empirically better than MSE. Then it comes to defining the meta-objective. So the meta-objective is defined as the average of these consistency losses over these different views. For each view, I basically mean the set of altered supervision labels for the batch, and you have m of them. So with the one-step look ahead, you will have something like this. Now this meta update for the student model is going to happen like this. And then it will be followed by normal training based on gradient descent of the conventional loss. And note that this is the actual noisy given labels. So meaning that those m views are used in this meta step. You'll basically regularize the theta and then you do the normal update. They also have this iterative training section, which means that they, first of all, do an initial training with the best validation accuracy. They call it Theta Star or Mentor Network. And they also filter out the basically the examples for which the given label is not associated with a high probability as the output of the mentor network. In other words, they feed the examples to the mentor networks. It's going to produce some probabilities for the outcome. If the label that is given to n is assigned a very small probability by the mentor network, it's going to be removed, which is defined like this. And then they do this averaging, so everything else is the same, they just do this averaging to involve the mentor network as well. They start with theta 0 and then ramp it up as the teacher network is improving, therefore this kind of helps with the stability, I presume. So going over the paper, they mentioned that they propose a noise-tolerant algorithm which utilizes meta-learning update prior to the conventional gradient update. And they do this by generating synthetic noisy labels and train the model such that after one gradient update, each set of the synthetic noise labels that are generated are utilized and the model should not overfit to the specific noise. In their words, they have a meta-learning based noise tolerant approach, which is called MLNT. So MLNT means meta-learning based noise tolerant. And their approach, like for example MAML, is model agnostic in nature because it does not have anything to do with the specifics of the model, and therefore can be applied to any method that trains with the gradient descent. And also they have a teacher model with a self-ensembling in order to create that regularizing target. So here's essentially the change from normal traditional training to their method, which means this additional meta update which helps not memorizing noise in learning the parameter set data. This figure also provides an overview of their system. As you can see, the student model is going to get an example, generate these synthetic labels. These synthetic labels are basically utilized for this method training step. They generate their predictions. You have a consistency loss here. You also have the teacher model, which takes the inputs and generate these outputs. So you would have the consistency losses between essentially these and have them as the meta loss. And also you have this classification loss in the original labels for the traditional update. And here you have the pseudocode for this algorithm. The main datasets they used was Cypher10 and Clothing 1M. Clothing 1M is an example of a dataset with real-world noise included in its labels. Here is the configuration they followed for the asymmetric noise adding to the basically Cypher. And here is that bit more on the experimental details. So they mainly focus on preact resonant 32, and here's more details regarding the implementation. One other important point is that they trained the approach for 3 iterations. The first one, so the mentor model is the best model from the previous iteration. And then they figured that beyond three iterations of training did not really lead to any significant improvements. The empirical results reported in the paper show that this method is superior to the other examples that they have compared against, including joint optimization and cross entropy. Now about the hyperparameters, here on figure 4, they show that basically increasing the value of m for each one of these basically noise rates, you can see that this bright blue is the highest value for m. You can see that there is generally an improvement associated with increasing this m. M again being the number of synthetic views generated. Regarding rho, or the ratio of items with the synthetic noise being added, you can see that the performance is relatively stable with different values of rho. This figure is for filtering out, so tau is that ratio, and you can see the larger value for tau means higher quality data but less cardinality for the training dataset, and the lower value means you include more examples. You can see that as the value of noise rate increases, then the optimal value for tau also becomes something that is larger than before. These figures also show that this approach led to better results. This is an example of the examples that are separated by the mentor model. You can see here that these are the actual ground truth, and this is the label that the mentor net assigned to it. They also showed that the results using this first order approximation is pretty close to the full approximation, therefore that first, one step look ahead is pretty useful. On the clothing 1M, also they got great results. In conclusion, this was a method learning approach to robustly train a model to perform a task given that the labels provided could be noisy.